start the recording here and then go to the full screen. Okay, so yeah, in the last class, I think I written down I made a mistake when writing down the Dirac delta function, the definition. So let me try to do this again and also take the chance to kind of like, you know, take everything in stock and see what we have so far. So because what we are doing is we are using the Hilbert space interpretation to understand quantum mechanics, right? And then we have been using the Hilbert space for two-level systems, two-state systems, two dimensions. We use it to solve masers and the Stern-Gallac experiment, right? So we have done this, and I hope everyone is familiar with that for the two-dimensional case. And once you understand two dimension, we can easily go to 3, 4, 5, right? But it's finite dimension. So now what we want to do is, well, position is still an important observable in quantum mechanics. Yes, position is still an important observable in quantum mechanics. So therefore, we try to use the Hilbert space to represent the states of position. I believe this is where difficulties, you know, things start to become more and more confusing, because instead of summing up the different bases, we use integration, right? So this is something that we are not used to so far. In your linear algebra, almost always you are using the finite dimensions, am I right? Like x, y, z, right? Or I, j, k. So always 3 or maybe 4. When we are doing special relativity, we have 4 directions, 4 bases, always finite. So it's sum 1, 2, 3, 4. But for position, right, if we don't have just 4 possible values, so it has it has all kinds of combination of 5. So okay, don't worry about 5D yet, but 4 dimension is, we have done this before, right? Don't worry, we have done this before, but we won't do it again. It's special relativity, right? Space and time. 4 dimension means x, y, z, and then the time, right? It's just including the t variable into your calculation, that's all, right? But we won't do this here, right? We are doing quantum mechanics now. It's worse than 4 dimensions. It's infinite dimensions, right? So what we want to describe is, I want to use the Hilbert space to describe this situation, right? So let's say this is an example of a state. So a state, let's say a particle is here, and a quantum particle can exist in many different states. So maybe you make an observation and you happen to discover the particle is in this position, right? I just picked some random number, 5.03 meters. So this is a state, right? So if this is a state, then I should be able to write this as a ket in Hilbert space. So if this state represents 5.03 meters, so I will try to write this, right? And this is a state in Hilbert space. It is an observable, right? So this is something that we do when we make an observation. So when we have an observable, it should have a corresponding operator, right? So operator for position, we'll just use the capital letter X, such that what you measure are the eigenstates. So these are postulate, I forgot now, postulate 3 of quantum mechanics, right? So it is an eigenstate. That means if this operator eats 5.03, if this operator eats this state, it is an eigenstate, so it will come back out again, the same state, and it will give you the eigenvalue. Okay, so this is what we call the eigenvalue of the state. So eigenvalue are the outcome of the measurement, right? So when you do a measurement, in some abstract sense, when you do this calculation, this number comes out. What does eigenvalue represent? Eigenvalue just means it is the number that is this number here, right? So this is the eigenvalue, right? So I remember in the previous class, some of you were a bit confused about what is the meaning of eigenvalue, right? It seems a bit abstract. You do operator and this thing, but eigenvalue is just a number that will represent I am doing what, right? The particle is doing what. Previously, the particle is I am spin up or I am spin down. Now we are talking about this variable. I am in this position. So this is what we mean by an eigenstate of the position operator, right? So this position x in is measuring the position of the particle. So I took one random number, but in general, of course, it could be any number, right? So that's why we write this equation, right? So this acted on this x, it will give you this eigenvalue depending on where it is, right? So you got like this, right? So the only problem is that this can take any real number. It's not just like up or down that is 2 values, or ijk that is 3 values. This is like infinitely many possibilities, okay? So but still, right, we are still talking about Hilbert space. The eigenstates of a Hermitian operator, this is Hermitian, okay? We can use it as a basis, right? So every time when we find eigenstate, we are always try to use those as a basis. So we can use the eigenstates as a basis. Okay, which is to say that my arbitrary state, this could be any superposition, could be anything, right? A particle under any situation. Well, I can expand this as a basis. So because this is like so many numbers, right? Instead of summation, we do an integration. Okay, so we do an integration of the coefficients times the basis. Okay, so this is to compare and contrast for the discrete case, right? For the discrete case, an arbitrary state is the summation over the coefficient, and then I'm using the basis. So you see, it is a compare and contrast, right? So the summation becomes an integration. The coefficient is here now, and then this was my whatever basis I am using. Okay, and in order to determine this basis, what did we do last time? So we just, for any Cj, I will just close this state with the corresponding j. If I want to find C1, I close it with C1. If I want to find C2, I close it with C2. Okay, so that was the discrete basis. Then this one is, well, it is a function of x. So to determine what is the value, we close this state with the bra-x, right? So bra-x, it will depend on what is this x. So when x is 5.03, it will give you the function 5.03. You will evaluate the function and give you what is the number, right? If it's at 4, then if it's 4, then the function at 4, it will give you some other value. Okay, so it's nothing, hopefully it's not too complicated. It's basically what we are trying to do when we want to represent the position of a particle using the Hilbert space. Okay, so this is a bit of a recap of what we did in the previous class. Oh, yes, yeah. That is true. Humans can only think of x, y, z direction, right? So 4 is a bit abstract. And when you go to the theme park, right, when they say 4-dimension movies, is there is a 4th dimension involved. In 4th dimension, it means the 4th component, which is the external senses, that kind of thing. So they shoot the water in your face, that kind of thing, right? Yeah, but in general, for the reason why they call it this is kind of the same thing. It's like in theoretical mechanics, you're gonna call it the degree of freedom, right? So there's different ways to experience or to describe things using 3 dimensions, 4 dimensions, things like that. Okay, so now it is infinite dimension because x can be any infinite number. So the basis is infinite. Okay, now the thing I want to clarify is the Dirac delta function. Right, when I did a few calculations in the previous class, I guess 2 compounding problems, right? I wrote instead of dk, I wrote dx, and then when we use the Dirac delta function later, it was I went a bit fast. So let me do it again, and let me explain this more clearly. Okay, so the mistake I did was the last time I wrote the wrong definition, right? So the Dirac delta function is defined to be 1 over 2 pi, and then the integral from minus infinity to infinity, and then I integrate with respect to k. Okay, it's supposed to be k. because after you integrate, it depends on x and x prime. So after you integrate the k variable, the final result shouldn't depend on k anymore. It should only depend on x and x prime. But it depends on x and x prime in a funny way, right? If x is equal to x prime, then if you integrate this, you just get an infinity. But if these are not equal, then if you do the integration, you will get 0. X prime. Okay, so if you do the calculation, and the reason is because you can expand this in terms of sine and cosine, and then the integral of sine averages to 0, the integral of cosine also averages to 0. So as long as this term is there, then you can become 0. But if this term is e to the power 0, you're integrating 1 from negative to positive infinity, so it's just infinity. Okay, so this is the Dirac delta function. And the reason why we want to introduce Dirac delta function is because the eigenstate is a basis. So if it's a basis, it must be orthonormal. So orthonormality of the basis requires that if I take any x and then I inner product with some other x, okay, if the x are different, then I want it to be 0. If the x are the same, then it is non-zero, but here we want it to be infinity. Okay, and the reason is because the area under this graph, you want it to be 1. Okay, so it's some technical requirement, but it kind of helps us it kind of generalizes the discrete case where we have the Kronecker delta. Right, so Kronecker delta, instead of infinity, is 1 if I equals to j, 0 if I not equals to j. Right, so the reason why infinity is because we will be doing integrations, and when we do integrations, we just want to make it equal to the area under, we want this area under the graph to be 1. Right, this is the height of this function. Right, if you plot a discrete, the height is 1, but this one, I want the area under the spiky graph to be 1. So that is the Dirac delta function. Okay, so that was a recap of position. And now let's talk about momentum. Okay, so the momentum is defined to be acting on this. So given a state, right? So given an arbitrary state, I say that I can expand this in the basis psi x and then ket x, right? And then the momentum operator is operator p. So it eats a new state, and then I will give it the outcome in the basis representation to be supposed to be h bar over I, and then differentiate this with respect to x and then x, right? So this is a new state, because a new state is the integral of I'm still online, right? It should be fine, because just now, this morning, when I connected, it kicked me off for no reason. That was before the class started, and I don't know why. It might be unstable. Monday is always the worst, right? It seems to be our experience. But in any case, we are talking about momentum operator eats a state, gives you a new state. What is this new state? Well, it is the state such that this will be my coefficient. My coefficient now is a function of x. It depends on all the different possible x over here. Okay, everything good? Yeah, convid. And our convid usually strikes on Monday for some reason. So so I will redo the calculation, because yeah, some of you have been asking me, but I think now that I write down the delta function properly, right, it should be k. I think now you understand, but just to be sure, let us find the eigenstates of P. Okay, so the eigenstates of P is, I want to find some state, right? So I'm going to call the state P such that if I eat if take the big P and eat this, it will just give me some eigenvalue times the same P again. Okay, so how do I find this? Well, I will use the trick that we will do quite often. I will just, for no reason, I will just suddenly say that, oh, P is just 1 times P, fine. And the completeness, I forgot to summarize last time, the completeness relation is to say that 1 is equals to the ket bra of x, and then I integrate over. This is the completeness relation. So we say that this is what we say, that this is inserting the completeness relation. Okay, so this is a common trick, right? So if you're confused, try to get used to it, because it will help us solve a lot of equations by doing this. In fact, it will help us find the eigenstates of P. So 1 is equals to this, right? So it is a P integral dx, ket bra x, and then the P is at the back, right? And then, well, this P is a scalar number, and this is an integral of x. So scalar number, so I'll just put it here. Okay, and this is what I'm looking for, right? So this is the momentum wave function of the eigenstate, position wave function of the eigenstate, right? So this is the wave function for the of eigenstate P, right? So this is what we are looking for, right? So what are the eigenstates? Well, let me rearrange this one more time because this is the coefficient now, and then this is my basis, right? So, and then I got dx, and then P psi P x, and then my basis is x, okay? And then I take the P and eat this function. So it will turn this into, by definition, becomes the derivative of x times h bar over I, and then this thing, well, nothing happened here, right? So this is integral dx, and then P psi P x, and then ket x, and we assume these two are the same because I'm integrating x. So comparing left hand side to right hand side, we come to the conclusion that h bar over I d psi dx is equals to P times psi, or we find that d psi dx is equals to I P over h bar psi. Okay, so this is a differential equation. So we can solve this by taking, this is the exponential function, right? So this is e to the power of IPX over h bar. Okay, so this is a constant, and we determine the constant by using the normalization. So we determine by normalization, right? So in other words, we should have these are the eigenstates P, right? So the eigenstates, we want them to be, we know it's orthonormal because we have proven this in chapter 1 already, but we just want to scale the length, the so-called length of the vector, such that the length is always equals to 1. So this is why we require that if I take the inner product, it's just going to look something like this, right? So P prime and then P. Okay, so I want this to be true. Okay, so I want this to be true, but what is this term over here? So let's expand. I insert the completeness relation again. So insert the completeness relation. I got P prime times 1 identity times P. So identity is actually the integral of the ket bra x. So x, this is P prime x P, right? So what is this? So this is the this first term is px, right? So this is px. Remember, this is the wave function. This is xp, right? So this is the complex conjugate. So this is a complex conjugate, right? so that you got e to the minus or negative ip prime x over h bar, and then this term is xp, so that's the normal one, so this a e I p x over h bar, right? So the a are constant, so I will move this out. Complex conjugate times a is just the absolute value, and then e and e I will group them together, so I got I p minus p prime. Okay, so I got this now, right? So how do we deal with this? Well, I will use the definition of the delta function. Okay, so the definition of the delta function was this, right? But now there's a h bar over here, but I hope you know how to do it. I will show you, right? So just to compare the definitions, this one has no h bar, integrate with respect to k, right? So this is changing the dummy variables. This is integrating with respect to x, right? So that means what I'm doing here is, well, look at this is the variable of integration, and then this is my variable of integration. Okay, so in order to compare the two of them, I'm going to let x over h bar to be my new variable, so that my dx is just h bar u. Okay, so that my integral now is becomes modulus a square. This one is h bar u, so h bar is a constant, so I'll put it outside, right? And then I got e to the power of I u, and then p minus p prime, right? So this was my definition of the delta function, just changing the variables a little bit. So this is equal to this, so this will becomes 2 pi delta p minus p prime, right? So that means I come to the conclusion that, well, I want continue this equation from previously. P prime minus p is equals to a square 2 pi p prime minus p, right? So this is, by the way, delta function is symmetric. So the negative sign and positive sign should be the same. Okay, so in other words, to compare left hand side and right hand side, you realize that a bar square is equals to 1 over 2 pi. So you can choose, because it is not a unique choice, right? A can be any complex number such that the absolute value happens to be this. So let's choose a real number for a, and then I got square root 2 pi. Okay, so finally, right? So finally, we can prove, we have found the eigenstates of P. Is given by, well, this is the P, right? This is the eigenstate, so this is the position representation of the eigenstate, and we have, hang on, I forgot the h bar, right? There's a h bar here, h bar, h bar, h bar. So I got 1 over 2 pi h bar square root integral of, wait, no more integral, is e to the power of ipx over h bar, right? Just to, yeah, I made a mess, so let me do it again, like this. Okay, so we have found the eigenstates of P. What do you mean? Well, I do agree that there's a lot of magic happening when you do this type of calculation, especially like the delta function and things like that, right? So any questions so far? Okay, now here's the thing, right? Every time I say, when we have an operator, let me check the system again. I'm recording. Yeah, so when we have an operator, we get the eigenstate. Once you got an eigenstate, we always want to use this as a basis. We have found the eigenstates of P. So can we use this as a basis as well? Right? So now this is the new thing. So now we have it's a momentum operator. And then we have found the eigenstates. So according to the postulate, the eigenstates form a basis, a complete basis. So we can use this basis. You can use this eigenstate as a basis. Also, right? Not just x, but also p. So that means given a state psi, right? Any arbitrary state in Hilbert space, I can use p as a basis. So instead of x, I'm talking about p now. So this will be psi using p and expanding with p as a basis, such that my psi p is, instead of closing with x, I'm using p now. And this is a complete basis, so it also has this relation, Tp, p, ket bra, p. Right? It's perfectly fine. So instead of describing the position of the particle, this is just the momentum. Okay? So here comes the thing where, the reason why I show you the video at the beginning of the class. It is the relation between the Fourier transform. So here's the thing, right? So this, I got the function, my wave function in terms of p, and here is my wave function in terms of x. So I got two different functions that represent the same state, this state, right? So this state, I can write the wave function using p, or I can write the wave function using x, right? If you're using x, means you're focusing on observing the position. If you're using p, you're focusing on observing the momentum. Okay, so these are two functions, but they come from the same state, so they must be related to each other somehow, right? So let us try to find the relation with position wave function. Okay, so again, I will use inserting the identity trait. So let's start with this statement. So this one is practically by definition, if I close this state with a p, I will get the value that is dependent on p. So it's a function of p, right? It is a complex function of p. So if you input momentum, it will give you the output. But now, for no reason, I will just say that this is 1 times psi, and 1 is, I will use the completeness relation for position. So p x x psi. Okay, and I have already derived this already, right? So we have done this already, and this is equal to this. So we have found that psi p, and what is px? So px was the complex conjugate of xp. There is a constant here, so let me take out the constant outside. Okay, and then the rest is integral dx, and then this is ei complex. Remember, be careful, this is xp, this is px, so I must complex conjugate this over h bar, right? And what is this? This is just the position wave function. Okay, so now you see that so now the relation is, this is actually a Fourier transform, right? So this is the formula for Fourier transform, but I will come to that later. But for just to reiterate, right, what we have here is, this is the momentum wave function. This is the position wave function. The position wave function is something that you have done in the previous classes, right? To probability of finding the particle between x equals to a and x equals to b, you absolute square this. This is the position wave function. This one we kind of seldom use here, right? And I'm almost sure you haven't done this yet, unless Prof. Ong did this already, I don't know. But we seldom use this here. But in the future, in more other research parts, people will start to use this, like in Feynman path integrals and things like that. So in quantum field theory, we use the momentum representation, right? So that means what we have here is we are plotting against the momentum, and then if you have the wave function square, then I can calculate the probability of finding the particle having this momentum from this number to this number, right? But this one is the familiar position wave function. If you plot this in x, then what's this sound? Yeah, I'm hearing the sound where I'm disconnected from Teams. But I'm still recording. Test. Yeah. A little bit lag just now. Yeah. I think I got disconnected and it auto connect me back. Okay, so the internet is not good today. Okay, but hopefully it's fine now. This is the position wave function. Okay. So now we know how to, this is page 1, page 2, page 3. So now we know how to relate given a position wave function. Yeah, given a position wave function, I can connect this to the momentum wave function, right? Depends on what we need. Okay, so I think if it's lag, I'll just continue going on. Otherwise, I will just like stop and stop all the time. Because I do have my backup recording still running, so at least we have that. Okay, why do I say that this is a Fourier transform, right? So this, okay, so let me call this equation 1. This is a relation between position wave function and momentum wave function. Okay, so equation 1 is a Fourier transform. So equation 1 is an equation for Fourier transform. So I believe this might be the first time you heard of Fourier transform. You might have done this in ODE. In ODE, I'm sure you did the Laplace transform, right? But what's a Fourier transform? So Fourier transform, well, let me show you the Fourier transform in the math definition. So the Fourier transform in math, if you Google or search Wikipedia for Fourier transform, this is what they will tell you. They will tell you that the Fourier transform of a function, right, is a function of k is given by 1 over 2 pi the square root integral from infinity to infinity with respect to dx e to the negative I kx, and then this function f. So given a function f x, I can Fourier transform into a new function that suddenly becomes a function of k, and it is related by this. Okay, so it is very similar to our equation just now, right? Except there is a h bar. So I'm going to let k is equals to p over h bar, right? So we got the familiar de Broglie relation, right? So if I let this, then what we have here is that my f Fourier transform is equals to this becomes p over h bar, and let me multiply both sides by 1 over h bar square root, so that I make the coefficients the same on both sides of the equation, right? And then this becomes dx, and then the k is just becomes e to the minus ipx over h bar Fourier transform of this, right? So this was our relation that we just derived. This is equation 1, right? So this is the equation 1 where this was my position wave function, and this combination is my momentum wave function. Okay, so it is the Fourier transform between the two. Okay. So now we can see, right, to get, you can go backwards as well. To get phi x from starting from phi p, we do the inverse Fourier transform. Okay, so phi of psi x is 1 over square root 2 pi h bar square root integral. Now you integrate dp, and then it's positive ipx over h bar, and then the momentum representation. Okay, so this is equation 2. This is a inverse Fourier transform. Okay. Okay, so now, yeah, so this is how we have been playing around with the position representation, and now we have figured out how to do the momentum representation as well. We have been playing around with infinite dimensional Hilbert space, and we have been talking about the Fourier transform, right? So I mentioned just now in the movie Transformers, one of the characters say that we should not consider Fourier transform. We should start doing quantum mechanics. But in quantum mechanics, Fourier transform is very important, right? It is a relation between position and momentum. Okay, so but I do get it. The reason why they say that in that movie, right, is because the characters are like the hacker trying to decipher the alien signal kind of thing, right? So it's a signal processing problem. Signal processing problem does involve Fourier transform in a different way. So whoever wrote the dialogue, right, is probably familiar with signal processing but not familiar with quantum mechanics. So that might be the reason why we got this type of people say these words in the movie. But yeah, in signal processing, Fourier transform is to identify the signals and the frequencies of a given sound, right? Some sound signal, your music, your things like that. What are the frequency that make up that sound? But what we're doing here is it's not sound, but it's position and momentum. Okay, but it's kind of the same thing, because now why does quantum mechanics position momentum involve Fourier transform, and why does the signal processing in transformers also use Fourier transform? Is because sound come in waves, sound waves, right? Sound are transmitted through waves. We have learned this in mechanics, right? We hear the frequency and things like that. So we analyze sound waves using Fourier transform. Right now, using quantum mechanics, we represent them using wave functions. So like electron interference, in the same way the wave interfere with each other. So therefore, the both sides are represented using wave equations, and that's why both sides use Fourier analysis. Okay. Make sense? Is it clear? Right. So that was a bit of infinite dimensional analysis. But now let's go back to what we are trying to do, right? We're trying to carry over our knowledge from discrete to infinite dimensional Hilbert space. So let us define a few more observable operators that will be important later. The next thing I want to discuss is the kinetic energy. Okay, so what's a kinetic energy? I did mention this in passing in the last class already. One of the issue, right? I want to how do we calculate the kinetic energy of a quantum particle? Well, kinetic energy originally was half mv squared, right? I need a velocity, but here we can't define the velocity. Of a state psi, because velocity is for particles. This is a whole wave, right? And for reasons that I will tell you later, we can't also use the wave velocity. So basically the v here is not the wave velocity, it's the particle velocity. So we cannot use half mv square to define this. Okay, even though the wave have a velocity, but you can't get a Hermitian operator out of this. If I can't do a Hermitian operator, then I can't do this operator as well. Okay, remember, kinetic energy is an energy. It should be an observable, so it should correspond to a Hermitian operator. Okay, so we can't do this, but we do have momentum, right? Momentum. So the kinetic energy, well, momentum is mv, so kinetic energy is going to be, we realize that p square is half mv square, so the kinetic energy is p square over 2m. Okay, so this is one way. So instead of expressing kinetic energy using velocity, this is ke expressed using momentum. So now we can we can sort of like quantize. We can quantize this. So using the quantum operator, P is h bar over I, the derivative. Then we define the kinetic energy operator as the following. Okay, so I can't use half mv square, but I do have this, right? So now kinetic energy, I can make this into a Hermitian operator, right? Well, this is 1 over 2m. Okay, then this is p operator square. Okay, so now it's like taking a Newtonian mechanic concept and turn this into a quantum mechanic concept. Means usually, most of the time we change this into an operator, but operator has a different meaning from the original concept already, because operator, remember, is always something that eats a state and spit out a new state. So what does operator square means? It means you're doing the process twice. You eat the state, you spit it out, you eat again, and you spit it out again. So you're doing it twice. So it is an operation, right? So that means h bar over I d dx, but you do it twice. Okay, so what you have here is, well, I got a h bar square, constant square. I times I gives you a negative number, and then this is 2m, right? And then d dx twice, it just means the second derivative. So what we have here is that my kinetic energy operator looks like this. Okay, so you start to see something familiar, right? You have seen this before. H bar over 2m. This is the part that appears in the Schrödinger equation. It is the part of the equation that tells you the kinetic energy. Right? So this is my kinetic energy operator. Okay, clear so far? Don't have any more, right? Don't have any more, but what you mean is this term, right? Schrödinger equation have this. Then yeah, it has. There is no half mv square in the Schrödinger equation. Is there? Okay. So that is true. There's no more half mv square. We express everything in terms of p, and this is the part that appears in Schrödinger. Okay, yeah. Then this is what happens. So we will come back to this later, but I will mention this in passing. So let me do a bit of a sidetrack very quickly. Okay, so I have a theorem. So even though we do not have half mv square, maybe I should write it down. Should I write it down? Because do you read? So I'm not sure whether you guys read the stuff I upload or you rewatch the video. So if you only watch the video, then I can just say, right? But anyway, even though we don't have V for quantum particles, we can do it for expectation values. Okay, so that's in other words, let's make a bit of space here. So shift this down a bit. There's a theorem that says that given a state with position expectation value well, what is the expectation value if I measure a position of a particle given some state, right? So it could be any state. So we do this, right? And I have shown you that the way to calculate this is take x and then psi complex conjugate in the position representation, right? Then if I know this, then the expectation value of momentum is calculating using this, right? Psi p, so it must be the same state, right? But we can prove that it is actually the derivative of the expectation value of the position. So this is almost like a velocity, right? So this is almost similar to P equals to mv, right? So it turns out that you can't define the P equals to mv just by the momentum, but the expectation value itself has the similar formula to P equals to mv. Okay, so I think actually I spent quite a lot of time recapping the beginning of the class, right? So we took up some time already. So I will not show you the proof here, but it won't be important in the immediate what we're doing immediately. So I'll just leave it in the lecture notes. So it is theorem 3.1.2 in the lecture notes. Okay, so yeah, the proof is just a messy calculation, and I got the impression that everyone understand the math part, right? The integration part, things like that, even though it's a bit tedious, but at least you understand the step by step. Okay, so that is what I got. Is the confusing part is the concept, right? So I should spend more time discussing the concept rather than doing the math, doing the step by step. So the only issue about this, using this theorem, right, you need to differentiate with respect to t. So that means we can only use this if we know how this function depends on t. So we can only use this if we know how the x, or well, if we know, yeah, one or the other is equivalent, how they depend on time. Okay, so otherwise we can't use it. Okay, so this one will be important, because whether this will be having a distinction, because later, right, what we're going to do next after this is we are going to have a time dependent Schrödinger equation, and then I will derive a time independent version of the Schrödinger equation. Okay, so yeah, so we have about 6 minutes before the break. So let's talk about another thing. Okay, so the reason why I do this is because I want to write down the Hamiltonian. Hamiltonian is kinetic plus potential. I have already shown you how to get the kinetic energy operator. How do we define potential energy for quantum mechanics? Okay, so this is the next issue that we want to address. 3.1.2, 3, right? So the way to define potential energy is, well, potential energy is a function. In Newtonian mechanics, potential energy is a function of x, right? It's a function of position. Remember, a spring is half kx squared, right? Gravitational potential energy is mg times the height. So it's a function of position. So I want to change this function into operators. In order to do that, we need to understand how to play around with operator valued functions. And from after we understand this, we can define potential energy. Okay, so actually is not that complicated. You will see what I believe is very easy after we kind of play around with this. So let's play around with the equation x, the eigenvalue equation, right? So we know this already, okay? And using this equation, we can easily define operator functions. So what do I mean? Well, let's observe that. Okay, so if I operate x on both sides, right? It's like multiplying both sides by the operator x. Okay, so this, like I said, right, this means this is operating x twice on my eigenstate. Okay, and then this little x is a scalar number. So scalar number, we can always push it to the front. Okay, but this one will just give me scalar number times x again. So what we have here is operator x twice. It will just give you the eigenvalue twice of this. So I think this is no problem, right? This one is quite easy to understand. So in fact, we realize that you can do this any number of times. In general, you can do it n times. Right? You can do this n times, and then you just get the eigenvalue n to the power n coming up. Okay, so this is like saying x times x times x n times. So this is what it means by operator to the power of x. Okay, so then let's see what happens if I take linear combinations. Okay, so yeah, let's continue here. So let's add to both sides. Okay, so let's see what happens if I add this to both sides. Then well, what we have here is x to the power n, and then I got big X times n, and then on the right hand side is xn x, and then the right hand side I will add to the right hand side, so it got x x. This is x, right? So we realize that, well, operators are linear, so I can factorize this. And then this one I can factorize this like this. Okay, so I can also add 1 to both sides. Why do I quote? Yeah, add 1 to both sides. Then so I think this is very clear what is happening here. If I add 1 to both sides, it's like plus 1 x, then it's just x to the power n plus x x plus x. So actually I can factorize this as well. Okay, so this is xn plus x plus 1. Okay, so you see what I'm trying to do, right? I'm trying to define functions of x, and this is actually equivalent to a function of the same function, but I change everything into an operator. Okay, so yeah, this is a function of x, of real number x. So this is like your calculus function, just like in calculus 1. Right? So these are function of x, just like calculus 1, but this is the new thing. So this is the new thing over here. This is what we call the operator valued function. Right? This is a real number valued function because you input a real number, you get the answer that is also a number. That here you input x, and then you get a new operator that does this thing to my state. So the output is an operator. So this is an operator valued functions, or in other words, we can also call it a function of operator. Okay, so if this is a function that we call f of x, then this is a function is f of big X. It's the same structure, everything the same, but I just change all the little x into the big X, into the operator. Okay, so this is how we define the potential energy. So in other words, given like a traditional or standard, like what you learn in calculus 1 function f of x, we can define corresponding operator function. So f of big X by replacing x with operator x. Okay, and it obeys this equation, right? So if whatever this is, right, x squared plus 1, x squared plus thing, whatever, it is a function of operators, but it will become a new function, right? So it will become a new function, and it will become a new operator. If you add this on the eigenstate x, it will just becomes the normal function, right? It will become the eigenvalue. So the eigenvalue is the value of this function. Okay, so this is just trying to change an ordinary function into an operator function. So now that we have an operator function, and with knowing that potential energy is a function of x, we can finally define the potential energy operator. Okay, so my potential energy operator is what? So firstly, we recall that in Newtonian mechanics, potential energy is a function of position, right? So in other words, potential energy V is a function of x, right? This is what we did in mechanics or high school or whatever, right? For the spring is half kx squared kind of thing. But if I go to quantum mechanics, then now it is the same function, but I replace everything using the operator, and it is an operator. And in particular, because all the x are Hermitian, linear combinations of Hermitian operators are still Hermitian. So it is a Hermitian operator. Okay, so yeah, so now we are almost ready now, right? We have learned how to so just a bit of a summary, you know, to put all the pieces together, right, before we break. So what we did was, since in the previous class we tried to represent Hilbert space using the position basis, right? And using position basis, and also we have learned how to calculate the momentum using the momentum operator, right? So we got position, we got momentum, we know how to relate the two, right? But most of the time we focus on position. But using the position basis, what is the kinetic energy operator, right? We know the momentum operator, so we define the kinetic energy is just p squared over 2m. So we know how to get the kinetic energy operator now. And then we just did how to get the potential energy operator. So once we have done this already, so after we come back, and maybe after some presentation, after the second half of today's class, we will finally define the total energy of the system. Okay, so that is what we are trying to do this entire time. We try to find the total energy of a particle, because that is going to be the Hamiltonian, right? So that's going to be the Hamiltonian. We will do that when we come back, but first let us take a 10 minutes break. Okay, so we come back at 10:10. Okay, so yeah, hopefully everyone is still following the story. it's not too bad, right? It's like I said, it's just new concept. So new concept takes time to digest in the brain. Okay. Yeah, so let's continue our story of the operator functions. Okay. So we're going to 3.1.4. Is it my screen? Yes. Yes, thanks, Kaixuan. Okay. So actually, right, now that I'm like thinking ahead of the future chapters, the difficult parts are at the beginning, and that there's a different, if you read different textbooks, right, you see like different ways they approach the subject. So other books like Griffiths, they start with the potential wells and things like that, some familiar things, but the calculations are difficult. So it's more like theoretical mechanics, right? The concept is there, but you need to do a lot of calculation, a lot of the steps there. But here what we are doing is we introduce Hilbert space from the beginning, right? We introduce the rules and things, so let everyone digest and get used to the rules. So by the time we use it to solve questions, hopefully we are more used to handling the bras and cats already. Okay. So later on we will still need to solve some potential well problems, and that is where we have a lot of math steps that might be, it won't, I don't think it will be difficult, but it's going to be long, right? It's just integration but with more terms, so we're gonna get a bit messy. So that is one thing we can prepare ourselves for the coming weeks. But first, let me introduce to you what is the Hamiltonian and the Schrödinger equation in position representation, right? So actually we already know the Schrödinger equation, but it looks a bit different from the Schrödinger equation you might have seen in other course, right? But I introduced to you the Schrödinger equation in Hilbert space. So how do I change from one form into another form? So let us, we start with what we have been talking about so far, right? So we have been talking about, we are talking about the position, and usually when we want to measure the position of particle, is usually referring to some moving particle of mass m, right? The total energy in Newtonian mechanics, so is, well, the E, right? So this one is not even year 1 mechanics, even high school, right? When you are still in high school, the energy of a system is kinetic energy plus potential energy, am I right? So kinetic energy, and we spent quite some time trying to transfer this idea into operator concept, and we do this by the P square over 2m, and then the kinetic energy is a function of x. Okay, so now also some of you guys, right, not everyone in this class, but some of you guys are taking theoretical mechanics, and you guys are asking about omega and things, so I think you are still solving about rotating frames. Later in the chapter, right, you will encounter Lagrangian first, and after you learn about Lagrangian, you will encounter a concept called a Hamiltonian. So when you reach there, it might be a bit confusing also, a lot of additional new concept and things like that. But at the end of the day, right, just to have something simple to imagine, the total energy is actually the Hamiltonian. That's it. So it will be called the Hamiltonian in theoretical mechanics. Okay, but there is some subtlety. Hamiltonian is something that is more general, but in the case where the system, if the potential is independent of time, you can prove that the Hamiltonian is exactly equal to the energy. So this is the case that we will solve in the next few examples. So that this is why we will encounter this as the Hamiltonian. So we're going to call this Hamiltonian. And again, if it becomes confusing, just remember that the majority of the situations that we solve, Hamiltonian is the same as the total energy. So Hamiltonian is an operator, right? So it is an operator that describes the total energy of the system. So that is all. That is all it means, right? So in quantum mechanics, the Hamiltonian, right? Hamiltonian is a function in quantum mechanics, right? It's an operator function. It is a function, but now we change it into operators. So the Hamiltonian is extended into an operator, or transferred, right? The concept we carry over into quantum mechanics by changing everything into operators. Right, so the Hamiltonian operator is basically just the kinetic energy operator plus the momentum operator. So it is 1 over 2m, and then the momentum square, and then plus the operator function. It will be a function of your position operator, and we call this the Hamilton operator. Right, it is Hermitian. Okay, because this will give us the total energy of the system, right? We have already encountered one Hamiltonian previously when we are talking about the ammonia maser, right? We attempted to derive or figure out a matrix for the Hamilton operator even before we understand the quantum chemistry and things like that. So using some general arguments without really understanding everything, we somehow got a Hamilton operator. That is quite amazing. But now we do it properly. Okay, if you have a particle that is moving of mass m, right, then this is the kinetic energy, then this is the potential. So the total should be the Hamiltonian operator. That the eigenvalues will give me the energy of the system. Okay, so this is the situation that we have for now. So now that we got the Hamiltonian operator, now we got x. Now we know how to express everything in position x. So we can now derive the new Schrödinger equation, the familiar Schrödinger equation, right? So the Schrödinger equation is now, how does it look like? Okay, so firstly, we are talking about Schrödinger equation where this is my energy. So this means for a particle of mass m, right? So the mass of the particle is taken into account here, right? Particle of mass m moving in a potential under potential v of x. So this will become here, right? And this will give the kinetic energy is given by what? Well, firstly, my original Schrödinger equation that is stated in postulate 5 of quantum mechanics is taking this form, right? So this is H operating on psi. So this is this is obeyed by the particle. But this H is given like this. So let us write this down here. So this is a momentum operator acting twice. This is some function of operator x. So all this combined will give you an overall operator, and this will act on the state psi. Okay. So the Schrödinger equation that you have encountered with Prof. Ong is using the x as a variable. So what I'm going to do is I will insert the completeness relation here, and I will change everything using x. Right, so I just insert one for no reason here, and I will insert one over here as well. So 1 over 2m p square vx, right, and then operator 1 acting on this. So inserting 1 means this is the ket bra x putting inside. Right, so this is ket bra x, right. So this becomes integral, and then 1 over 2m p square plus vx, and then this becomes the ket bra x, right? And I have shown you that this is giving me the position wave function, right? So this is my position wave function. So this is actually position wave function with the basis. So what I got is dx I h bar d dx position wave function, right? And then in the basis x, and then the same story happens here. So this is dx and then 1 over 2m p square plus v x, right? And then the position wave function, and then acting on x. Okay, so should I include the details? Yeah, let me do it very carefully, step by step. Wait, you guys said the steps are okay, right? But anyway, what I'm trying to say is, if I multiply this out, right? So what do I have here? So what do I have here is 1 over 2m. Remember that p square is negative h bar square, right? And then I got the second derivative, right? And then this one acting on, so this one I can change this back to my traditional Newtonian function of x, right? And then this is acting on the basis x. So notice that well, I got IH bar d psi dx in the basis x is equals to integral dx, and then this is h bar square. So if I write it this way, it means it's like multiplying inside the brackets. So it's d psi dx square plus v times psi, right? And then basis x. So the integrals are the same, so we assume that the integrands inside shall be the same because this is for arbitrary x. So what we have here is IH bar d psi, hang on, why do I write x here? This is differentiate dt. Why do I write x here? This is dt, right? This is the time derivative. This is the x derivative. Okay. So the time derivative on the left hand side, and then this is h bar square over 2m. Okay, this is d square d psi dx square, and then plus v psi, right? So this is the Schrödinger equation that you might have seen before, before learning about Hilbert spaces. So this is the Schrödinger, so we call this the Schrödinger equation. How do we get this? Well, everyone here is a function of x because we are using the x as the basis. So this is the Schrödinger equation in the position representation. Okay. So now you see the familiar face, hopefully, right? But for those who did not take Prof. Ong's course previously, it's not familiar, but now mind, right? We are doing it as if we are doing it for the first time, right? So we come to this equation again. Okay, is this clear? Right? So yeah, actually, like these steps are what you meant by, you know, are not, the steps are okay, right? It's just to, you know, linking the concepts and things like that. Is that what you meant? So, but in any case, we will be, for this chapter, we will be spending quite some time solving this form of the Schrödinger equation in this position representation. Okay, so we have derived this Schrödinger equation, but this, at the moment, right, what we have here is it is a partial differential equation. So it is a PDE instead of ODE, right? So it is a partial differential equation involving two variables. Right? It is a function of t and it's a function of x. Okay? So it will be difficult to solve this straight away, but what we do is, well, we can simplify this equation a little bit. And our strategy is, this is a partial differential equation with t, derivative x. right? So what we're going to do is I'm going to separate this out into an equation for x only and an equation for t only, right? So this will bring us to the time independent Schrödinger equation. Okay, so this is our next step that we want to do next. Hang on. Okay, so how do we derive the time independent Schrödinger equation? So let me write down the equation again, right? So so my wave function, right, my position wave function is now, well, it is a function of position, but we want to describe how the state changes over time, right? So in general, as time goes on, the probability distribution of the particle might change, right? It depends on the situation. It might not remain the same. So it depends on x and it depends on t. So it's a two-variable function, right? So this should be a solution to my Schrödinger equation. The psi dt is equals to h bar squared over 2m, second derivative, and then v psi. Okay, so this is a partial differential equation, right? So I'll just call this SE, Schrödinger equation. But let me simplify this equation by using the concept of separation of variables. Okay. Actually, have I shown you separation of variables before? I don't remember whether we did this in EM. But the key step is we will it is a function of two variables. Let us assume or pretend, what if, even though it's a function of two variables, it is just a multiplication of this function of one variable times another function of just one variable x. Okay, so if this is true, then what happens if I substitute this into my Schrödinger equation? So can I solve this by assuming? Okay, so this is assuming, right? Like for no justification, but if I can get a solution, then fine, that's great, right? So if I assume this is true, then I substitute. So if I substitute this into the left hand side, this is a differentiation of t. So that means I just need to differentiate this term. This term doesn't depend on t, so it's not differentiated. So I got I h bar psi. Then I got d phi dt. Okay. Then the same story happens here. This is a differentiation of x. So only this part depends on x. This part doesn't depend on x. So this part goes outside. And then I'm differentiating this function with respect to x. Okay. And then this one is nothing. Psi is just phi times psi. So I got this, right? And then in the next step, I will divide both sides. So I want to separate. Remember what we're trying to do, right? So I do this, and then what I'm trying to do is I try to push everything depending on t to one side and push everything depending on x to the other side. So the way to do this is I will divide both sides by the whole thing, right? Psi times psi. So if I divide both sides by this, right? So what happens is this will become I h bar over phi d phi dt equals to this one is h bar squared over 2m. This is 1 over psi d psi dx, and then divide, it will become v. Okay, so this will achieve what I'm trying to do. So I am pushing everything to the left hand side. All this, right, everybody here is phi t. So everybody here are functions of t. So it depends on t only. Okay, then on the right hand side, you see that everything on the right hand side, it depends on x only. So everyone here depends on x only. So this is the key concept of the separation of variables. Just by manipulation, I manipulate everything so that all here depends on t only, and everyone here depends on x only, then now I am faced with this possible contradiction. How this is a function of t, this is a function of x, so it depends on t and it depends on x. These t and x are independent variables, right? These are two different variables. So how can a function of t be equal to a function of x? Okay, so this is the core point of separation of variables. So let's try to think about this. I know that when I learned this as a student for the first time, I took a while to digest this as well, right? So how can a function of t depend on x? So t is like a time, right? X is a function of x. So if something depends on t, that means a few seconds later it might change into something else, right? But the right hand side depends on x. So on the right hand side is a function of x, then a few seconds later, how can it still be the same function of x? So the only possibility for left hand side equals to right hand side is they are both equals to a constant function, right? So this combination is a constant, this combination becomes a constant. Okay, so the only way for if I want left hand side to be equals to right hand side, right, t only and x only, it implies it means both sides are constant functions, right? So an example of a constant function is fx equals to c, right? So you just get a constant function, right? So you know what I'm talking about, right? They are both equals to a constant function. So that means these two are equal, happen to be equals to the same constant, so that left hand side equals to the right hand side. So I'm going to let the constant be called E, because we already know the spoiler that the E is going to be the energy of the system. So in other words, what we have here is I h bar phi d phi dt is equals to the constant E, and also h bar squared over 2m 1 over psi d psi dx squared plus v is also equals to the same constant. Okay, so if I rearrange this, both equations, so just to make it look nice, I have d phi dt is equals to negative IE over h bar times phi, and then I rearrange, I just bring the psi up on both sides, so I got h bar squared over 2m d psi dt plus v psi is equals to E psi, right? So now I derive two differential equations, and these two are differential equations that depend only on one variable. So now I got two ODEs, so easier to solve, right? So what we have here is we had two variable partial differential equations, which was equation SE, right? This is a two variable partial differential equation, has been split or separated into two single variables, which is equation 1 and 2. Okay, so that will make our life so much easier to solve. Yes, correct. This is a trick I use a lot, so sometimes I use without saying. Yeah, suddenly there's a negative come out, right? And the reason is because yeah, remember this. So 1 over I is I over I times I, so it's I over minus 1. So I will always use this trick. Yeah, complex number, you guys are not too used to it yet, right? So it's the kind of thing that we can play around. One of the things to play around with. Okay, what time are we at now? Well, we have about 2 minutes left. But actually, we have separated into two ODE. In fact, right, this ODE, look, this one is a simple equation. So equation 1 can be solved immediately. That is pretty amazing because we haven't even specified what is the system yet, but we already can get half. We can solve half of the problem already, right? So IE over h bar phi. This is a derivative is equals to a constant times back to the function. So the solution is an exponential function. So it's e minus IET over h bar. Okay, and I will not put the integration constant here because I will there is an integration constant the integration constant will be absorbed into the equation for absorbed into the psi x part. Okay, there's a constant there, but because at the end of the day my solution is going to be phi xt, and then I got psi t and then psi x. So there is a constant. So this solution is constant times exponential IE t over h bar, and then the constant I haven't solved what is psi x yet. So so we will worry about the constant later, right? But the important part is how this depends on t. So it just depends on the exponential function, IET over h bar. What do you mean? What? Well, the class end now lah. I just finished what I wanted to say. Yeah, I guess so. But in any case, we have already partially solved the Schrödinger equation. All that remains is just need to do this, right? So we just need to solve the remaining Schrödinger equation that is over here, right? So this E is going to be the same E that appears here, right? So yeah, so over the next few classes, we will see how to solve this equation. Well, no way for our lecture. Yeah, I'm bet everyone is starting to feel hungry now, right? It's going to be 11. In any case, I guess it's a good time to stop to here, right? A lot of new concept for you guys to digest, but I think on Thursday class, we will stop it for here now, because on Thursday class, I will just say a few more just clean up a few more concepts about this, and then after that, we will solve a very simple problem, which is the infinite potential well. Right, so it is a very simple solution that you have kind of already solved in the ODE classes and things like that. So we will encounter the problems. So from then on, hopefully it's going to be a bit more smooth running. Okay, so yeah, so for that is Thursday. And to reiterate, right, our plan for our midterm shall be the Monday slot. I think no objection. Then we shall proceed with this, right? Because yeah, end your suffering earlier, and also to avoid timetable clash with other classes. So that's all for today, I guess. Let me stop the recording.